Hello everyone, this is Gavin, and today we'll be talking about the first tool for analysis called the Completeness Axiom for the real number and even some of its consequences. It serves as a foundation of the real analysis, especially for the boundedness of the real number and some of its subsets, for example, the integers. So to study the boundedness, we have to know that there are two parts of it. The first one is, suppose there is the set S, which is obviously a non-empty set that is a subset of a real number. And we know that S is bounded from below. Then we know the infinite of S exists. What does it mean? The infinite of S means the greatest lower bound. So we know that if bounded from below, it means that there is a number, for example, we call it C. There's a number C having the property that for all of the X in S, X is greater or equals to C. I write it this way. There's the number C. In real number such that for all X in S, we have X greater or equal to C. And we call that bounded from below. And this C value is called the lower bound. So we know the greatest lower bound is called the infinite. And similarly, we have the concept of the least upper bound, and it can be defined by another way. We call it, there's the empty, non-empty set of the real number, and if it's bounded from above, then the supremum, which is the least upper bound, exists. We write it exactly in a different way. For all X in S, X right now is smaller or equal to C. We just write it in an opposite way. So in the graph, you can see from the range, from the set of the all real numbers S, if it's from -3 to -2, and it's open on the left and closed on the right, we can see that the greatest lower bound is -3, and the least upper bound, which is supremum, is -2. And it is very interesting to know that it doesn't need to be inside a set in order to be a lower bound or upper bound. As long as it fit a property that I showed on the right side, it is a lower bound or upper bound. So what about the integers? There's the very interesting concept called, if we're analyzing an integer, there's the non-empty set of the integer, and if it has no minimum, then it is bounded from below. How do we prove this concept? Prove this conditional statement, we need to assume that the premises, which is S, it has no minimum, is true. And then we try to build a bridge between the premises and the conclusion that we're shooting for. So because we know that S is not empty, therefore for sure there's at least one element in it, we just call it X1. And X1 is not a minimum of it, because we have already assumed the premises is true, which is S has no minimum. Therefore we know there must be existing another element inside S. We call it X2, and X2 has to be smaller than X1, because X1 is not a minimum. And because X1 and X2, by assumption that they're both inside a set of integer, we know that integers, X2 has to be smaller than X1 minus 1, because of the basic properties of integers. And similarly, we can find another element by the same reasoning, we call it X3, that is inside a set of integer, but also smaller or equals to X2 minus 1. And if we keep going, you can find a pattern that for any n integer n, which means n can be 1, 2, 3, and so on, and we can find there is some xn subscript n that is inside S, such that for all of the k inside integer, we can find that x to the subscript of x plus 1 is smaller or equals to x to the k minus 1. And this general idea is derived from what we call induction, because this is what we know from above two steps. And by induction, we know all of the m that is inside integer, we have the x of 1 plus m smaller or equals to x1 minus m. So you see, we can always find an element that is inside the set, but also smaller than the previous element we find. So if we can keep going and going and be smaller and smaller, S is obviously not bounded from below. So this is true. And you see, when we analyze an integer, it's quite different from what we saw in the real number case showing above. So this is the critical distinction has to be memorized precisely in order to do more analysis in the future. Thank you so much.